Okay, I'd like to welcome everybody to the SLT millimeter wave learning series, our free EMF educational series discussing 5G radiation and millimeter wave. Today's topics include the effects of EMF and millimeter waves presented by Lloyd, the effects of RF and millimeter wave sources presented by Magda. Then we have Rob and Bruce are going to introduce us to the millimeter wave meter and the difference of 5G frequencies and measurement protocols. And we have Keith, who's going to do new discoveries of millimeter wave sources. And then last but not least is Orem, and he will be doing the hunting millimeter wave towers in Southern California. So without any delay.
The next speaker will be myself. And also one of our product developers, Bruce Hildesheim. So he'll be joining me at the tail end of that presentation. And then we'll have Keith Cutter and Orem after that. So I will go ahead and grab the screen and start the presentation. Okay, so I am Rob Metzinger, and in case you have not met me before, I'm the founder of Safe Living Technologies and been involved with building biology for years and years. I'm also electronics engineering technologist, so yeah, as a techie guy, this sort of thing kind of piqued my interest years ago, and attracted me to this area or this field of business. And yeah, we've been at it for about 20 years, and just continue learning every day. And all these presentations just help build all that information and just keep you going in the forward direction. We're in an industry of flux. It continually changes, and we're continually learning new things. And just like with these millimeter waves, we're learning what devices transmit them, how to measure them, and so on. So it's just another thing we have to figure out and thing we have to learn to deal with. So I'm just going to give you a little bit of background about our millimeter wave meter that we've just put out on the market in the last month or so, and show you how it operates and tell you a little bit about the development of it as well. So for a brief introductory video, I'll just pop this up. It's our YouTube video on our website, and it'll give you a basic introduction to what the meter can do for you.
The new Safe and Sound Pro millimeter wave meter is the first consumer level 5G millimeter wave meter. This meter measures high-band 5G signals between 24 to 40 gigahertz and comes with multiple accessory options for more detailed readings. These options include a horn antenna, a stub antenna, and an attenuator for various uses. To start the unit, press and hold the power button. After that, your battery level will appear on the screen. The mode and max reset button will allow you to capture your maximum values of RF exposure. Now you can attach your desired antenna. To start, we will be using the stub antenna. The stub antenna is ideal for most uses. It has about 50 degrees of coverage in the front and back. It is suggested to slowly move the meter around in a figure-8 motion while in use. The horn antenna is great for more directional measurements. It has about 35 degrees of coverage in the front. Finally, the attenuator is ideal for when your RF readings are maxing out the device. If this happens and the attenuator is not installed, the meter will display a brief message and automatically shut off. When the attenuator is attached, it will display the readings as 100 times weaker, so you are able to measure at higher power levels. When measuring RF sources using the attenuator, ensure you multiply the value by 100 to attain the correct reading. Overall, the Safe and Sound Pro millimeter wave meter is the perfect partner to the Safe and Sound Pro 2, our low and mid-band 5G meter. For more information on the new Safe and Sound Pro millimeter wave meter, the Safe and Sound Pro 2, and other EMF mitigation products, please visit our website at www.safelivingtechnologies.com.
Okay, so a little bit about our meter there and a little bit about the development of the meter as well. In order for us to do this in a reasonable amount of time, we had to construct our own full anechoic chamber so that we were able to test signals. It allows us to test signals from around 700 megahertz all the way up to infinity. So way up in the high gigahertz range. And this is a full anechoic chamber, which means the ceilings, walls, and floors are shielded with this anechoic foam. A lot of the testing sites out there are semi-anechoic chambers, which have metal floors. And with millimeter waves, it causes a lot of reflections and it can really skew the reading. So we wanted to do this right. We wanted to be in an area, we wanted to have this in an area where we could just develop something, go in and test it, develop something, go in and test it. So we had that right at our fingertips. So that was a great help in designing this meter. Bruce can attest to that later. So we also purchased our own signal generators, power meters, and spectrum analyzers from 1 megahertz to 40 gigs, so we could do all this testing as well. So if we wouldn't have done this, we'd still be waiting for this meter. So it just really sped up the development of the meter for us. So a little bit about the meter. The base model is the standard model that we have, and it covers 20 to 40 gigahertz in the high band of 5G RF. And so the USA 5G band covers 28 gig and 39 gig. So we wanted to make sure we could cover both of those bands. It's live in major cities. Verizon, AT&T, T-Mobile, and Dish transmit those signals, and you need a special phone in order to access those frequencies. In Canada, we're looking at 26, 28, and 38 gigahertz millimeter wave bands, but technically they're not deployed yet, we don't think. We are finding some surprises out there. So we expect the auction to be in 2024 and more to come in Canada at that period of time. But we are finding readings out there at this point in time. They could be test sites, they could be other millimeter wave sources. So we're still investigating that. So they're called millimeter waves because of their wavelength that's underneath 1 centimeter. The industry calls them, as Magda said, ultra wideband UW or 5G plus. Those are the symbols you're going to see on your phone if you're connected to that service. And for the base model with the stub semi-omnidirectional antenna, which is a great standard antenna to use, is $849 US. And we did release this on June 30th. They are in stock and online and ready to go at this point in time. We did have a large pre-order list, but all of those are fulfilled, so we're caught up with that, and they're in stock, ready to go. For more information, you can just click on that when you view the digital PDF of this presentation to get there if you like. And some of the features. So there is also a horn antenna, as you can see on the left here. The stub is a semi-omnidirectional and the horn is a directional antenna. And both of these detect and measure 5G in the millimeter wave band, covering 20 to 40 gigahertz. Common sources, high band cell phone towers, high band cell phones, radar, automobile radar, point-to-point communication dishes. Discover what more is out there. They're built in North America. We're very, very proud of that. And they're consumer level and affordable. So accurate and affordable and a fraction of the cost of these spectrum analyzers and other high band detectors out there. And also, I think we have higher sensitivity than most meters out there as well too. So the digital display displays in microwatts per square meter and volts per meter, and also average. It has a peak hold feature, and response time is less than 50 microseconds, so still picking up fairly quick signals. And battery life is another challenge. We're getting about 6 hours with sound on our meter, which is adequate and good. The audio feature we have as well. So it's similar to the Safe Sound Pro 2. Each source has its own unique sound, and we have 3 volume levels on this meter as well. We also wanted a way to indicate your measurement quickly. And kind of like our Pro 2 and Classic, we included the LEDs, the 4 colored LEDs, and you can see the what each color represents there on the right in that chart. And basically you look at the meter if you want a quick understanding of your exposure. Green is good, red is bad. So that's one quick way to do it as well. Understanding the reception patterns of the antenna are critical, especially in building biology use. If we look at the horn first, it's directional, so it has about a 35-degree beam width on the front, and it only measures to the front, not to the back. So it'll measure left side, left, right, a little bit up and down, but about a 30-degree cone or beam. That's kind of how you define the reception pattern on the horn. And with the stub, it's semi-omnidirectional, and it's got a 50-degree beam width to the front back. It does measure from the front and from the back, and this beam width is left, right, up, and down as well. So you can kind of see the space where it's gathering RF signals and information from and compiling those numbers, putting them on the screen. And it also has some side lobes too, so it does pick up some from the side as well, not as well than it does from the front. So that's basically the reception pattern for that semi-omnidirectional meter and our antenna. And this stub antenna will also yield higher readings than the horn antenna. And for obvious reasons, it's just gathering more energy from more directions because it's a semi-omnidirectional antenna. So looking at a little bit about the specifications. So the stub antenna or semi-omnidirectional antenna, it's got a frequency response of plus or minus 5 dB from 20 to 40 gigahertz. And it's also effective down to 18 gigahertz with reduced tolerance. So the smallest signal it can measure is 5 microwatts per square meter. And the highest measurable signal without an attenuator is around 500,000 microwatts per square meter. The best reception, this antenna has an SLT logo on it. So you want that logo facing outwards and a blank side facing you as the operator of the meter. And that will yield the best results in your measurements. The horn antenna, the directional antenna, it has a frequency response plus or minus 6 dB from around 25 gig to 40 gig. It is more sensitive. It goes down to 0.5 microwatts per square meter, and the maximum measurable signal would be about 30,000 microwatts per square meter without the attenuator. And this was all customized. This was all part of our research and development, making our own horn antenna that's compatible with our meter and works in this frequency range. So that's all customized for SLT. Then we have the attenuator, which is good. So I would have liked to measure a little bit higher than 500,000 microwatts per square meter. So we came up with this antenna design. It's a minus 20 dB attenuator or 100 times signal reducer. So you attach it between the antenna and the horn, or between the antenna, the horn, or the meter. And basically, when you get a reading on this, you'd have to multiply the display by 100. So it allows the meter to display higher power density signals by a factor of 100, and the range up to approximately 2 million microwatts with the stub antenna and the attenuator, and approximately 120,000 microwatts per square meter with the directional horn antenna. We did have those values a little bit higher before, and just to err on the side of caution, we just wanted to lower that a little bit. Bruce can explain a little bit of that as well when he takes over the presentation. With this attenuator, so it's a built-in power overload protection, and so the RF detector circuit is susceptible to damage if exposed to continuous high levels of RF. It is unlike our other meters where that's not a concern, but in this case, in the millimeter wave band, it is a concern. So we had to build in this overload protection, and is activated when the following power densities are exceeded. If the stud exceeds 500,000 microwatts per square meter sustained, and the horn antenna exceeds 30,000 microwatts per square meter sustained, we kind of put the meter into shutdown state. And the meter will power down after 3 seconds of elevated exposure and displays a warning message, over power, and simply install the attenuator if you want to measure these high power density readings. And you can do that safely with the attenuator. So the actual operation of the meter, just looking at the startup screens, this is the startup screen. And first it does a self-calibration. Then it shows your battery life, and you can also run continuously if plugged into a USB-C power cable. And it will say where the BAT number is here. It will say USB instead of the percentage of battery. That's how you can tell that you're active and you're running on USB power. So the second screen that comes up is the antenna selection screen, and the antenna is selected via the mode switch, which is this button right here. And when you press the mode switch, it will toggle this arrow from stub to horn or vice versa. And basically, once you've selected the antenna you like, hold the mode button down for 3 seconds, and that will select and set your desired antenna for the time that the meter is powered on. When you power it off, you'll have to do this reset one more time. So the different measurement types, the front panel, we have peak, we have max of the peak, and we have average. So these are the three types or modes of measurement that we've incorporated into the meter. And it also has a headphone jack, 3.5 millimeters, so you can listen to it in private if you like. And then we have the power button here, basically holding it down, turns the unit on. And then once the unit's on, it acts as a speaker on-off button with 3 levels of sound. Then we have our USB port here, where you can plug it into USB power and monitor continuously. And then we have the mode selection switch to select antennas. And we have, this doubles as a max reset button. And also if you hold it down for a period of about 5 seconds, it'll change the units of measurement from microwave or from, microwatts per square meter to volts per meter. So we do offer 2 units of measurements with this device as well. And some future meters that are coming down the pipe, we're thinking about 200 megahertz to 8 gig, as well as the 20 to 40 gig meters. So having 2 in 1, or just developing a 8 gig to 20 gig meter as well. Exactly. And then also thinking about the high band of Wi-Fi, which is in the 60 gigahertz range. So having a 40 to 60 gig meter, and even higher than that, 60 to 90. We're going to need that for some of the car radar, which I'll show you in the next few slides here. We're up actually into the 76 gigahertz range for that. So we're also looking for suggestions and compiling these new meter designs and starting to march forward with them as soon as we're able to. So here's a quick demonstration of a millimeter wave in action, actually measuring a vehicle. So it's an RF vehicle scan, and in this case, it's 2020 Lincoln Nautilus SUV, and I will just go ahead and play this and show you what we found here. Hi, this is Rob at Safe Living Technologies. Today we're going to take our millimeter wave meter into the field and do some testing. 20 Lincoln Nautilus. It's a higher-end vehicle. It has a lot of the bells and whistles, and we're going to use the millimeter wave meter to see what type of radio frequency waves are coming off this vehicle. So I'm going to turn on the meter. I'm going to use the stub antenna, and I'm going to turn the volume on. Car is currently powered off, and you can hear that hissing noise right now, and the value is less than 5 microwatts per square meter. So that basically means there's no signal present at this point in time. So what we're going to do is we're going to take a loop around the vehicle just to make sure that nothing is emitting when the vehicle's off and our background levels are fairly quiet. So we just went down the driver's side, now we're coming around the back bumper. Approaching the passenger side. And moving up things are still quiet. I would expect to hear sounds coming off of this as well if we're getting digital pulses coming off the car. Now we're at the front bumper, we're moving around the front of the vehicle, and it seems to be quiet. There does not seem to be any emissions coming from this vehicle as it's turned off. So the next step will be to turn on the vehicle, and we'll repeat this measurement process. All right, so we're repeating the process with the car turned on. So the automobile is idling, it's in park. So let's go around the vehicle and see what the readings are. See if we can detect any RF in the millimeter wave range coming off this vehicle. So we're moving down the driver's side, going towards the back of the vehicle. Still looks pretty stable. Actually just picked up a reading now, so I'm going to turn up the volume here so we can hear it as well. And it seems like right around the back bumper here, you can probably see one of the sensors down here as well. This is kind of where we're getting our highest readings, right in this general area. So there's definitely emissions coming out of this part of the bumper. This is the driver's side bumper, rear bumper. And we'll go towards the middle of the tailgate. Really nothing there. I'm going to hit the reset button, clear the values, and then go over to the passenger side bumper. And we can see the same emissions coming off the passenger side bumper in this location too. So now we're moving, I'm clearing the peak, and I'm moving around to the side of the vehicle. And once we get to the back passenger door, it seems to go away. So it seems to be transmitting out of that rear bumper on the left and right hand side. And that makes sense because it's a blind spot sensor. That's where your blind spot is. And that is what it's supposed to do. So just making rounds to the front of the vehicle. It's still running, and we don't see any emissions coming off the front at this point.
Huh.
Okay, sorry about that. I just got popped out of presenter mode there. So yeah, there you have it. Vehicles emitting microwave radiation in the millimeter wave band. Hi, this is. And so what can we do about this, or what direction can we turn? So each of us, if we go to our owner's manual and service manuals, under the customer information heading, there's something called radio frequency certification labels. I found this very interesting. I haven't found it until I just started investigating this in the last few weeks. And for this particular vehicle, here's a list of the radio frequency certification labels in the service manual. And it lists them, it lists the licenses transmitting certificates for the various countries and for the various frequencies and systems that it uses. So very good piece of information to look at, and you can do that with your own car to see what your car is producing. So once you open those up and get into that, I opened up the blind spot information system sensor part of this, and I was able to find FCC and Industry Canada certifications. So if you type in those numbers in the FCC website and Industry Canada website, it will give you a ton of information about the transmitters, and most importantly, it'll tell you the frequency of the transmitters. So I looked this up, and it came out at 24 gigahertz. So there are places you can find information about this on any vehicle, and it's in the owner's manual and service manuals.
Huh.
So looking deeper into this document, and these documents, this SUV contains 10 FCC certified devices / RF transmitters. This was news to me, but here you can see by looking all these up, it took me about an hour and a half to do this, looking up all those FCC certificates, going into them and looking up the frequencies. We can see all the frequencies here that are being emitted by this vehicle, and we can cover some of them. We can't cover all of them. To cover all of them will be our goal in the future, but this just gives you an idea of what's out there. And this was for a Ford Lincoln. So I'm going to go out there on a limb a little bit and say probably a lot of the new Ford vehicles or Lincolns as well probably have all these in common, because manufacturers wouldn't switch between 2 or 3 different types of transmitters. You know, they would go with the same ones. So that's the information I found. Hope you guys find that useful. And so I thought, well, I got this emitting from my vehicle and I want to get rid of it. So how do I get rid of it? So if you go into the on-screen menus and you go to the driver's assistance screen, you would think that if you unchecked blind spot recognition, which I did, that 24 gigahertz signal would stop coming out of my bumper, but it didn't. So this I need to play around with a little bit more to try and understand how we can disable some of these items, but it doesn't appear you can disable that. So these are the other items that to be concerned about: the cross traffic alert, the cruise control, the driver alert, the lane keeping system, and also the pre-collision system as well. So all of these are possible candidates for transmitting microwave radiation in the millimeter wave band. So that, I just wanted to bring that important piece of information to your attention. And this the next item is kind of a little bit of a sidebar, and then I will pass it over to Bruce here. But you know, in our previous seminars and webinars, Orem has discovered millimeter wave signal travel through glass to some extent. We have pretty well proven that they have difficulties going through ceilings, walls, and floors, and other pieces of metal. So how do we shield our home and automotive glass surfaces? So Signal Protect Clear window film, there was this discussion at the end of the last webinar on how effective it would be. So I asked some of the guys in our shop to do some quick tests for us. So Signal Protect Clear is an option. So a quick performance test on it. So what we did here is we had a 26 gig transmitter. We cranked it up to 31,600 microwatts per square meter. And we are using our Safe and Sound millimeter wave meter to measure the strength of the signal. Then we're inserting a piece of shielding material 2 inches between the two and seeing what the results are. So what we did is first of all, we wanted to make sure that this was a valid test and it worked to our, it worked well. So what we did is we stuck a piece of aluminum foil or aluminum foil shielding in between it. And we know it has very high attenuation capability. So we wanted to see a near zero response, and we did. So the aluminum foil resulted, you know, with a source of 31,000 microwatts per square meter. The meter said less than 0.5 microwatts per square meter. So there's a greater than 50 dB reduction with aluminum foil. It's actually probably up around 100 dB. But you can see the reduction here. And then we did the same with our Signal Protect Clear film, and it allowed 4.69 microwatts to come through that film. So it ended up in a minus 38 dB shielding attenuation, which is pretty good. So we're pretty confident that Signal Protect Clear will block these signals coming through glass. It's easy to install in flat glass in homes, but it's more of a challenge in automobiles. But it gives you some options anyways, just sitting in traffic and in bumper to bumper traffic with all these millimeter wave signals. It could definitely reduce your exposure inside of a vehicle. Okay, so that ends my presentation. So I'm going to pass this along to Bruce Hildesheim. He's part of the SLT product development team. I've been working with him for over 10 years now. He's classified as an analog and RF specialist, and he will be discussing the millimeter wave meter and millimeter wave measurement strategies as well. Bruce, I have you up on the next slide here with your flow chart, and please continue on.
Okay, great. Thank you, Rob. Thank you, everyone else. Rob, if you could just put me on the camera. I just want to do a brief introduction for 1 minute before we look at this slide. If you could just, I don't know if that's possible for you to exit out of your presentation mode for a moment and then come back a minute later.
Sure. Okay, Orem, can we blow Bruce up there?
How about maximize the video?
Well, I stopped your screen sharing, Rob. Bruce, go ahead.
Yeah. Okay, great. Thank you. I should be on there right now. Again, Thank you, Rob, and everyone else. It's truly wonderful to see these people here. The last time, or maybe the previous time, I was in an anechoic chamber, and now I'm in the exact opposite. And I wanted to just show this to people, just to show I was an electrosensitive person myself, and this is where it all started. I was one of Canada's youngest licensed ham radio operators, and I was exposed unintentionally to a lot of RF because I trusted the industry safety standards. And later on in my life and my career, I came across with David Giesel, another engineer, and the two of us are co-inventors and developers of all the safe and sound products. And I knew Rob since 2014 when I really discovered that I was electrosensitive. And so if there is some good that comes out of adverse situation, Lloyd mentioned that his experience was kind of inspiring to hear his experience, because I'm more sensitive than ever, but I'm not suffering the symptoms because I know what to do with it, or know how to mitigate these things. So I can still use this equipment, but I'm aware of what to do to protect myself. And I hear somebody's microphone on.
I muted them.
Okay.
Can everyone who's not a speaker, please mute yourselves? Thank you.
Okay. So that's how it started. So if there is some good that comes from adverse situation, like in the case of Lloyd, look at what he's doing. And in the case of this, if it wasn't for my electrosensitivity, quite honestly, the safe and sound meters wouldn't exist. And as Rob mentioned, it was quite a process to come up with a mmWave meter, something that was very sensitive and very accurate. And so, Rob, if you could go back to that, or Orem, if you could put Rob back to screen sharing, and then we'll go back to that slide again.
Rob can do that.
Okay.
Gotta find it again on his desktop.
Yeah, it's
Sorry, Rob.
it's vanished on me. I'll get it.
There it is.
There it is. Yeah, we got it. Okay. All yours.
Great, right. So Rob mentioned in the presentation, initially when we released the product, we with the attenuator, we had much higher levels that this meter could measure with the 20 dB attenuator. In other words, multiply your screen readings by 100. We decided to lower that value until we can do testing. One thing that you'll notice, and since I've been involved in the development and manufacture of these meters along with David Giesel, is that we wanted to always provide, and Safe Living as well, wanted to provide lab certified, lab tested equipment. In other words, especially now in the future when we have medical professionals involved in this, in mitigation and measuring to diagnose and to help understand what's happening, lab certification and lab testing qualification is extremely important. So the reason we're lowering the maximum levels to the 2 million microwatts per square meter with the stub antenna, or 120,000 somewhere around there with the horn, is that that's all we can test at the moment. That's the maximum amount of RF millimeter wave power we can generate at the moment in the chamber. Now we're looking to increase that so that we can properly test that. So the reasoning for lowering is just simple, that we don't want to release specifications for a meter unless we're absolutely certain. So the other thing is, if you're in an environment where you've got multiple millions of microwatts per square meter coming at you from the semi-omni antenna, you've got to be concerned whether it's a few million or 10 million. You definitely have an issue that needs to be looked at. So I won't talk through this flow chart in detail, but the idea behind this chart is to encourage people to use the semi-omni antenna as the tool, as the antenna for measurement, Why? Because a semi-omni antenna, or ideally a perfectly omnidirectional antenna, is the closest thing, I think, to a human body. A human body is not a horn antenna. We don't only pick up RF from certain directions. Our body picks up everything, just like Lloyd touched on. And so what we did here, what I did for Rob, was make this flow chart. It's like, just a process to go through that. Unless your power measurements are above a certain level, don't use the attenuator. There's no need for it. So we're starting with the omni antenna, and then you go to, is your measured level that you're seeing greater than 500,000? If not, then take your measurement. Now, the horn antenna comes in handy. You might have a measurement in a few 100,000 microwatts per square meter and don't know exactly where it's coming from. Well, at that point, you can switch to the horn antenna, and then you can use the horn antenna to find out where it's coming from. But again, I would like to say that if your measurements are strong enough to measure something with the omni antenna, with the stub antenna, that is the antenna to use. Okay, so I won't go through the whole flow chart, but the idea is with these light green triangles, you answer question yes or no, and you just follow this. So Rob at Safe Living can make this flow chart available, I think, on the website. I would just like to touch the purpose in the bottom left, the purpose of the omni antenna. It's used primarily, it's used for measurements in consideration of total body exposure. So that's the antenna to use. And the horn antenna is used for point source detection, direction finding, okay, or measurements, or if you're in an area that's so fringed, some of the maps that Magda showed in New York City, for example, if you're in one of these fringe areas that there might be some millimeter wave, but it's not strong enough. In other words, the measurements from the stub are below or near 5 microwatts per square meter. Well, sure, at that point, then the horn is very useful. You can put that on and get some measurements, right? But again, the idea is that the horn is used only when there's no other, when the stub antenna can't measure anything. And then the horn antenna turns this meter into an extremely sensitive device that can give you some more information. But as I've mentioned a few times, in consideration of total body exposure, and I think for valid building biology guidelines, the stub antenna is the way to go. And also, the stub antenna offers the greatest frequency range, covering from 20 to 40 gigahertz. And, based on the frequency response plot that we've tested, even some useful information down to 18 gigahertz. And the horn antenna has got amazing sensitivity, and it has its place, but the frequency response is reduced from 25 to 40. So I just wanted to clarify that. But I think that's it, Rob. And thank you, everyone, for taking your time to listen to this. And it's truly inspiring that the work that I've done here and the work that we've done, that I've done with David, and my experience really suffering with problems from electrosensitivity, that experience could turn into something positive. And to see these tools out there in public being used by people and helping people is truly inspiring. Thank you.
Thanks very much, Bruce. Always appreciate your technical input.